What if you could design, optimize, and visualize spacecraft trajectories with the speed of C++ and the simplicity of Python and MATLAB? Epicycle is a new Julia ecosystem that brings mission design workflows from preliminary concepts to multi-event optimization fast. Epicycle is 11 specialized packages for space mission simulation and design built to take advantage of modern scientific computing, a complete rethinking of what's possible. Let me show you what makes it different. In this video, I will introduce you to the Julia programming language, describe and demo Epicycle, and show you where to go to be up and running in minutes. So why Julia for aerospace? Because it solves the two-language problem that's plagued scientific computing for decades. Julia is performant, near C++ speed. It's scientific, built from the ground up for technical computing. It's differentiable, automatic differentiation is native. It's AI-ready, modern machine learning tools are first-class citizens. It's parallel, built for modern hardware, and it's intuitive, syntax that feels like Python or MATLAB. At the heart of Julia's scientific ecosystem is SciML, scientific machine learning. You get state-of-the-art differential equation solvers, optimized linear algebra through BLAS and LAPACK, symbolic analysis, modeling tools, inverse problem solvers, and a massive numerical utilities library. And the aerospace community is already here. Differentialequations.jl is the gold standard for trajectory integration. Optimization.jl and Snow.jl connect to major solvers like SNOPT and IPOPT. Julia GNSS for navigation and positioning. Julia Astro for astronomical calculations and ephemerides. Satellite Toolbox and Julia Space Mission Design contain low-level models and algorithms, and Epicycle provides an application interface for aerospace engineers to solve hard problems fast. This isn't just another tool, it's a rethinking of how to work with modern languages and tooling built from the ground up with modern computer science technology. Fast iteration, modern algorithms, and AI-assisted development, all in one language. Now let's talk about the Epicycle architecture overview. So how is Epicycle structured? It's 11 packages, each solving one specific problem. At the foundation is Epicycle Base, it contains core types shared across everything. Then the primitives, AstroEpics for precision timekeeping with multiple timescales and formats, AstroStates for orbit state representations, Cartesian, Keplerian, whatever you need. AstroUniverse for celestial bodies, constants, and ephemeris, and AstroFrames for reference frame transformations. Next, the mission elements. Astro Models defines spacecraft. Astro Maneuvers handles impulsive maneuvers. Astro Callbacks provides the calculation infrastructure for constraints, events, and I/O. Then the computational engines. AstroProp for high-performance propagation with event detection. AstroSolve for numerical optimization. It interfaces with IPOPT and other major solvers. Finally, Epicycle itself, the integration layer that brings it all together, including the 3D graphics. Each package is independent. You use just what you need, or you can use the whole system. It's modular by design. All right, let's have some fun. I'm going to show you rapid-fire demos that start from low-level utilities and go all the way through solving an 8-segment trajectory using IPOPT. Here I'm in VS Code showing the workspace, or in Julia, the REPL, which stands for Read, Evaluate, Print Loop, with Julia running and Epicycle loaded. Let's start by creating a time object. Notice here we can see the time value, the time scale, and the time format. Let's convert the time to barycentric time. Now let's take a look at the Julian date. How about the modified Julian date? Let's add a half day to the time. Time is stored using two numbers to ensure nanosecond precision. Let's inspect those. Now let's create a Cartesian state. Now let's convert it to Keplerian elements. Now let's access some of those elements. Now let's create a state in the incoming asymptote state representation. Now let's access the help system. We first enter question mark, and then we type the name of the struct we would like to inspect. And finally, let's look at all supported state types. Now let's build on that. Let's define a spacecraft, providing the state, time, and a name. Now let's define a simple propagator that uses Earth, Moon, and Sun gravity and a standard Julia built-in numerical integrator. Let's propagate the spacecraft for 1 hour. Let's define a simple impulsive maneuver. Let's apply the maneuver to a spacecraft. Let's inspect the spacecraft state. Let's propagate backwards. Let's inspect the spacecraft history that contains the ephemeris. Let's grab the last state vector from the ephemeris. Let's access the last time in the ephemeris. Finally, let's view the trajectory in 3D graphics. Now let's add some complexity and solve a problem. First, we'll reset our spacecraft. We already created a maneuver. Now let's declare its delta v vector a solver variable. Now let's define a constraint function on the magnitude of the position vector of the spacecraft. We'll define the constraint to be 42,000 kilometers. Now let's connect the physics to the optimization. Here we'll define a maneuver event. Here we define an event to propagate to apoapsis. Now let's create an event sequence, add our events to the sequence, and call IPOP to solve the trajectory. Now let's inspect the solution. And finally, let's view the solution in 3D graphics showing the solver iterations. Let's wrap up the demos with a more complex example. This is a complete geotransfer optimization, a low Earth orbit spacecraft performing 3 maneuvers to reach geostationary orbit. The code sets up a trajectory sequence with 8 events: propagate to the equatorial plane, execute the transfer orbit insertion maneuver, coast to apogee, perform a mid-course correction, then the final circularization maneuver to place the spacecraft in geosynchronous orbit. Each maneuver's delta V components are optimization variables with bounds, and constraints ensure we hit the exact target orbit. IPOP solves this multi-event trajectory optimization automatically and can visualize the entire solution in 3D. So let's run it. The initial release of Epicycle focuses on architecture and is built for extensibility. Every package follows consistent design patterns: modular, composable, and testable. Testing is automated and continuous. GitHub Actions run the full test suite on every commit. Testing has been performed on Windows, macOS, and Linux, and at the time I'm making this video, coverage is at 94% across all packages. We've validated Epicycle against packages like Astropy and GMAT for numerical accuracy. I'm excited about the initial release, and I'm already working on functionality for the roadmap in the next release. Upcoming functionality includes coordinate systems, force models, optimal control transcriptions, and navigation. Getting started is easy and only takes minutes. There are links below for how to install Julia, how to install Visual Studio Code, and how to install Epicycle. There are also links to the tutorials and examples to get started fast. Epicycle ships with comprehensive documentation. The homepage gives you the complete picture, architecture overview, package descriptions, and clear comparisons with other Julia aerospace tools. Getting started walks you through installation. Add the package, verify it works, and run your first example. After you install Julia and VS Code, installing Epicycle is literally 2 lines of Julia code. The tutorial section contains component cheat sheets and end-to-end examples. The component cheat sheets show you how to set up time systems, how to set up orbital states, how to define a spacecraft, how to define celestial bodies, how to configure maneuvers, and how to configure calculation astro callbacks, which are used in stopping conditions and constraints for optimization. End-to-end examples show you how to propagate spacecraft, how to apply impulsive maneuvers, how to solve problems such as the Hohmann transfer or a complex geostationary transfer. The graphics and visualization documentation show how to render trajectories, how to render CAD models, how to render celestial bodies, how to show optimization history in the visualization, and how to render multiple spacecraft. In the component documentation, Epicycle packages are grouped into logical groups like foundation packages, physical models, and mission design. In each package, we begin with a quick start guide for getting up and running quickly for that particular package, and have reference material. For example, here we have propagator configurations, how to configure stopping conditions, how timescales are handling, and each package has a comprehensive reference API that documents all functions and structs. Thanks for watching. In this video, I introduced Epicycle, a new Julia package for aerospace. Below, you'll find complete links to the GitHub page, documentation, installation guides, working examples, and ways to reach out with feedback or questions.